So in this video, we're going to be looking at how you can recover the results from Coulomb's law and finding what the electric field is from a distribution of charge from using Gauss's law for cylindrical systems. So we already actually saw this when we first derived Gauss's law and we started talking about some charge, some point charge, and the electric field that comes from it. Now we know from Coulomb's law that E vector is equal to 1 over 4 pi epsilon naught q divided by r squared times r hat. Now, in this case, what we wanted to do is we wanted to show how we could use Gauss's law to come back to this same result. And the way that we did that was we exploited the symmetry of the situation. So, to remind you, Gauss's law says the integral of E dot ds is equal to q in divided by epsilon naught. And so, because this electric field exhibits some spherical symmetry, what we want to do is we want to draw some Gaussian surface around this to make use of that. And the Gaussian surface that we would use would be a sphere. Because the ds vector is going to be in the same direction as the E vector, which means that the left-hand side of Gauss's law can reduce to E times S, where S is the surface area of the sphere, so this is going to be equal to E times 4 pi r squared, which is going to be equal to the charge that's contained within that sphere, which is just going to be this q that I have here. So this is q divided by epsilon naught. And so when we rearrange this, Gauss told us that this would be 1 over 4 pi epsilon naught q divided by r squared times r hat when we recover the unit vector from the ds vector. Okay, so we saw a very important result here, and that was the fact that when we apply Gauss's law or when we just use Coulomb's law, we ended up getting the same electric field. And this was for just our point charge using spherical symmetry. But now what we'd like to do is we'd like to do the same thing with some cylindrical symmetry. And that's to say, if I have some charge density of lambda that's uniformly spread, and this goes from negative infinity to infinity, we'd like to find what the electric field is some distance r from the this wire with this charge density. Okay, so the first way that we're going to try to do this is we're going to apply Coulomb's law for infinitesimal pieces of charge. So this would say that this would be some dq, and there would be some. Now I'm not so happy about calling this r. Let's call this y. There's some dq, this is some distance x, this is the distance from here to here that we call r, and so what we can say is r is going to be equal to the square root of x squared plus y squared. And we know that the equation that we want to use here says that dE is going to be equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. So we've already actually found what r is. Now what we need to do is we need to find what r hat is. So r hat, as always, is the unit vector that points from dq to the point where we're finding the electric field. We can define some angle here, theta. And then what we see here is that r hat is going to be equal to cosine of theta x hat plus sine of theta y hat. And then we can replace cosine and sine with the appropriate trigonometric ratios. And so this says that the cosine is going to be equal to x divided by r x hat plus y divided by r times y hat. The last thing we need to do is parameterize what dq is. We know that in general, dq is going to be equal to lambda dl. Here we actually just have explicitly what lambda is. And dl, because this is spread over the x-axis, is just going to be dx. So this is lambda dx. Okay. Now to find what this electric field is, we just need to put all of this together in order to evaluate the integral. And so to do that, we say that this is E vector is going to be equal to 1 over 4 pi epsilon naught times the integral. I have a factor of r and a factor of r squared here, so that's going to give me an r cubed, where r is the square root of x squared plus y squared, and so this is x squared plus y squared to the 3 halves. lambda times dx times x hat plus y hat. And because this charge is spread from very far away on the left to very far away on the right, we're going to say that this integral is going to be evaluated from minus infinity to infinity. Okay. Now, typically this is not the kind of integral that I would ask students of mine to actually evaluate because it requires U substitution or trig substitution. But because I actually want to get exactly what this integral is to be able to compare it to the Gauss's law answer, we are going to evaluate this. But the first thing that we can notice here is when I integrate this in the x direction, so the terms that are multiplied by the x hat, I'm going to get 0. You can see that for a couple of different reasons. One reason is the fact that for every charge on this side that has some electric field that points this way, there's some charge on this side that has an electric field that points the opposite way. So it cancels via symmetry. The other more mathematical way to think about this is to consider the fact that x as a function is an odd function over the interval that I'm integrating over. So it's odd across the origin. So if I integrate an odd function over an even interval over the origin, that's going to give me 0. And then this x squared plus y squared to the 3/2 is an even function across the interval. So that's to say that it has mirror symmetry across the y-axis. And so when I multiply an odd function times an even function and integrate over an even interval, that's going to give me 0. So there's two ways to think about that. I think for us it's a little bit easier to think about just the symmetry. For anything on this side, there's going to be something on this side that cancels the electric field produced from here because it's a uniform distribution of charge. Okay. So now, we're not going to evaluate that, but what we are going to have to evaluate is this integral. So we have E vector is equal to 1 over 4 pi epsilon naught times the integral from minus infinity to infinity of y hat lambda times dx divided by x squared plus y squared to the 3/2. Okay. Now, the way that you're going to evaluate integrals of this form is to use what's called the trig substitution. And that's to say, I'm going to ultimately be exploiting the properties of sine squared plus cosine squared theta is equal to 1. Or specifically in this case, this is going to be, if I divide both sides of this by a sine squared, that's going to give me a 1 plus a tangent squared theta is equal to a secant squared, cosecant? Divide this by cosine. So if I divide this by cosine, this one's going to be tangent squared, this is 1, and then this is going to be a secant squared. Okay. So what we can do is we can say that x is going to be equal to y times tangent of theta. And if you don't see this, this is okay. This is just a technique for integration. And then additionally what we see is that dx is going to be y times the derivative of tangent. So this is going to be d of sine of theta over cosine of theta. I think this is a secant squared, but I'm just checking it because I don't remember exactly. So this is going to be a This is going to be, well, we can do this like this. So quotient rule says I take the denominator squared times the derivative of the numerator, which is going to be a cosine of theta, times the denominator. So this is going to be cosine of theta. So that's a cosine squared of theta, minus the derivative of the denominator. Derivative of cosine is minus sine theta, times the derivative of the numerator, or no, just the value of the numerator. So this is going to be sine of theta. And so ultimately what we have is cosine squared plus sine squared. That's 1 divided by cosine squared. So yeah, this was what I thought it was. This is just going to be a secant squared theta d theta. Okay. So now what we can do is we can do this replacement. The other thing that we need to do is we need to modify our limits. So if x is minus infinity, what we can do is if we plot what tangent looks like, tangent from minus pi over 2 to pi over 2 looks like that, okay? And if you don't see that, that's okay. What you can do is consider the fact that tangent is sine over cosine. What happens when this goes to pi over 2? This is going to give me a 1 divided by infinity for 1 divided by 0, which goes to infinity, and then when it goes to minus pi over 2, it goes negative 1 in the numerator and 0 in the denominator, so that one's a negative infinity, effectively. So we can rewrite this integral here as E vector is equal to 1 over 4 pi epsilon naught times the integral from minus pi over 2 to pi over 2 times y squared times a y squared times a secant squared of theta. I want to take my time here and make sure I don't make any mistakes. So this is a y hat, a y squared, a secant squared theta, a lambda, a d theta, divided by, and you'll see why I made this substitution in just a moment. So when I divide this by the denominator here, I'm going to have a y tangent of theta quantity squared plus y squared to the 3/2, okay? So I have a y squared common to both of these factors. I can factor that out, and because it's y squared to the 3/2, that's going to be a y cubed. That's going to help me with this this y squared here, and we're not actually integrating over y or lambda, so we can write this on the outside. So this is going to be so this is going to be y squared lambda y hat divided by 4 pi epsilon naught times the integral of secant squared theta d theta. And now the denominator here is just going to be tangent squared plus 1, but we saw up here that tangent squared plus 1 is secant squared, and so we're going to have a secant squared to the 3/2, that's going to be a secant cubed, so this is going to be a secant cubed of theta from minus pi over 2 to pi over 2, okay? And now I'm gonna move up here and work over here. So secant squared divided by secant cubed is going to be 1 over secant, and 1 over secant is going to be cosine. So at the end of the day, what we're going to have here is E vector is going to be equal to y squared lambda y hat divided by 4 pi epsilon naught times the integral of, why didn't I have y squared? I made a mistake. Or I just left something off. There should be a y cubed here. So there's a y cubed, and so that's going to make this a y in the denominator. Okay. So this is good so far. Minus pi over 2 to pi over 2, cosine of theta, d theta, and this is an integral that we can do now. And so the integral of cosine is going to be sine of theta, so this is sine of theta, evaluated from minus pi over 2 to pi over 2. This is going to give me a factor of 2. Right, because this is going to be 1 minus negative 1, which is going to give me 2. And so at the end of the day, after all this trouble and substitution with this calculation, what we end up seeing is that this electric field is going to be lambda y hat divided by, this factor 2 cancels a factor 2 in the denominator, and so this is going to be 2 pi epsilon naught y. Okay. So that's the hard way to do this, and actually why I wanted to go through this, to show you that if you have the opportunity to exploit the symmetry of the problem, you should do that, because it makes your life a lot easier. So after doing this whole messy calculation using Coulomb's law, let's see how we can do it with Gauss's law. So start, as always, by just writing down what Gauss's law says. And actually, I know I don't need a lot of room for this. So Gauss's law says the integral of E dot ds is equal to Qn divided by epsilon naught. And I'll put my lambda here again, and this is the point y that I want to find the electric field at. And so because we know that the electric field is going to radiate radially away from my wire, the natural choice to make here is to draw some Gaussian cylinder, okay? Because again, always the game that we're trying to play with Gauss's law is to get our E and our ds to be in the same direction. It simplifies this. So at the end of the day, when we make that simplification, this is just going to be E times S, the surface area of the outside. These two end caps are going to give us a zero contribution to the flux because the electric field is perpendicular to the dA vector. So now, if I say that this is going to be some length of L for my cylinder, this says that E times S is really just going to be E times 2 pi, this is some radius of y, E times 2 pi y times L. Okay? Now, how about the right side of Gauss's law? Well, when I cut this lambda charge density by drawing this Gaussian surface, what I can say is that Qn is just going to be equal to the lambda, the length of the line charge density, times, or sorry, lambda, the line charge density, times the length that is inside this Gaussian cylinder. And we see, when we look at that, that's just going to be the length L. So this is going to be lambda times L, and we're one step away from being done with the calculation. And so that's just to say, put all of this together and then evaluate for the electric field. So when I do that, this is going to say that E vector is going to be equal to 1 over 2 pi y. My L's are going to cancel. Lambda divided by epsilon naught times y hat. And this is written in a slightly different way than I ended up writing it over here. But you see that these two are the same thing. Now, given the choice of, you know, somebody locks you in a room and says you can't leave until you calculate what the electric field is for this line charge density. Given the choice, are you going to toil through and do the Coulomb's law way, or are you going to apply Gauss's law and do it in 3 lines? All right, so that's going to be it for this video.